Before, in the previous video, we were dealing with gas laws having to do with volume. So how things affect the volume, how pressure affects the volume, how temperature affects the volume, and how the number of moles of the gas affects the volume. But what if the volume doesn't change? Before, we were talking about examples where we had helium in a balloon and how the pressure uh, made the balloon either increase or decrease in size, in volume, or the temperature made the balloon increase or decrease in size, or the number of moles of the gas made the balloon increase or decrease in size. But what if the volume is not, we're not dealing with a balloon, we're dealing with a rigid container, so the volume stays the same. So what if the volume, the gas is in like a box, a metal box. So metal is not going to get bigger or get smaller, it's metal, it's going to stay the exact same. So the volume is the same. So what if the volume stays the same, but one of these factors, the pressure and the temperature, if one of those is changed, what's going to happen? Well, there is a French scientist by the name of Gay-Lussac, and he figured out that the pressure and the temperature, the P and the T, they affect each other. If the volume stays the same, the pressure and the temperature can still alter each other. So when the temperature goes up, the pressure also goes up. And when the temperature goes down, the pressure also goes down. So when you heat something up, if it's given that the volume stays the same, if it's in like a rigid metal container, not a balloon, but if the temperature goes up and the volume stays the same, then the pressure is going to increase if it gets hotter. If the temperature goes down and the volume stays the same, the pressure is going to go down. If it gets cooler, the pressure goes down. And so that gives us this mathematical formula. The pressure that you start with, the P1, divided by the temperature you start with, the T1, is going to equal the final pressure, the pressure you end up with, divided by the temperature that you end up with, that you heated the gas up to. So let's do a practice problem with this example. A 30.0 liter sample of nitrogen inside a rigid metal container at 20 degrees Celsius is placed in an oven whose temperature is 50 degrees Celsius. The pressure inside the container at 20 degrees Celsius was 3.00 atms. What is the pressure of nitrogen inside the container once it is heated to 50 degrees Celsius? So what is this question asking? Let's go to the end of the question where it has the question mark, and it says, what is the pressure of nitrogen inside the container once it is heated to 50 degrees Celsius? So this is our second temperature. Our first temperature is the 20 degrees Celsius, what we started out with. So our first temperature, the temperature we started with, is 20 degrees Celsius, 20.0 degrees Celsius. And our second temperature, our ending temperature, what we ended up with, is we heated it up to 50 degrees Celsius. So that's our T2. So 50 degrees Celsius. Now it has also, it says the pressure inside the container, the pressure inside the container at 20 degrees Celsius was 3.00 atms. So at 20 degrees Celsius, that was our first temperature, right? So when it was 20 degrees Celsius, when we had T1, the pressure was 3.00 atms. So that's going to be P1. And then the question asks, what is the pressure of nitrogen inside the container once it is heated to 50 degrees Celsius? So once we have T2, the 50 degrees Celsius, what is the pressure going to be? So that's going to be P2, and that's going to be our question mark. What is the pressure going to be when it's heated up to 50 degrees Celsius? Now, what about the volume in this question? We start out by saying the volume, a 30.0 liter sample of nitrogen. So the volume is 30.0 liters. But it says inside a rigid metal container. So this volume is not going anywhere. This volume is not going to change no matter what you do to it because it's a rigid metal container. It's not a balloon. So we can go ahead and assume that this volume stays the same. So we don't need to use this 30.0 liters in our calculations because the volume doesn't change. So this is unnecessary information. We don't need to deal with that. So when we're doing Gay-Lussac's law, that's the P1 over T1 equals P2 over T2, we have our P1, which is 3.00 atmospheres, divided by our T1, which is 20 degrees Celsius. But remember, we need to change this to kelvins. So 20 degrees Celsius plus 273.15 equals 293.15 kelvins. So that's going to be, our T1 is going to be 293.15 kelvins. And then that's all going to equal our P2, which is our question mark. So we're going to put down X for P2, over our T2, our final temperature, which is 50 degrees Celsius. So if you add 50 degrees Celsius plus 273.15, you're going to get 323.15 kelvins. So we're going to put that down for our T2, 323.15 kelvins. Now, how are we going to solve this? Well, we can take our 3.00 atms and divide that by 293.15, and that's going to give us 0.0102336688. And that's going to all equal X over 323.15. So we need to get this X by itself on one side of the equal sign. So the way we can do that is we can multiply both sides by 323.15. These cancel each other out, and we go times 323.15 over here on the left side, and that gives us 3.307010077, and that's going to be the pressure, so that's going to be in atmospheres. And since we're dealing with three significant figures, we can round this to 3 sig figs, which is going to equal 3.31 atmospheres. So 3.31 atmospheres is our P2, our second pressure, once the sample of nitrogen is heated to 50 degrees Celsius.